So today we are introducing the topic of rational functions, and then within that we're going to talk about the end behavior, the horizontal asymptotes, and slant asymptotes from those rational functions. So first off, what is a rational function? So a rational function is the quotient of two polynomial functions. So when you take two polynomial functions and you divide them, that's a rational function. You can kind of see down here, these are some examples, right? We got a polynomial on the top and a polynomial on the bottom, right? Same thing, one in the top and one in the bottom. They look really, really scary, but we're going to break them down as this unit goes on, and they're not going to be as bad as they look. Okay, so one of the big things today is we're going to talk about a whole bunch of different vocab of different things, and then we're going to focus in on finding just a few features of these graphs. We're going to kind of build the whole thing as we go along in the unit. So the first bit of vocab that we have is an asymptote, which you should have talked about before in Algebra 2. So an asymptote is a line that a function always approaches, but never actually reaches. Okay, now there is a small exception to that. Your graph actually can cross the asymptote. That is a thing that they are allowed to do. But as you reach the ends of the function, it's always going to approach that line. Okay, so as you look at kind of these graphs down below, you can see these dashed lines. These are asymptotes. So as this graph kind of comes out and goes out forever, it's approaching that line. It's not going to keep going like up and up and up and up like a line does. It's going to kind of level out and approach that. And you've done asymptotes like this before with exponential functions in Algebra 2. Right? So we're also adding in vertical asymptotes. So you can see on this vertical line right here, right, the graph is approaching that asymptote and approaching the asymptote on this side. Okay, so that's all that an asymptote is. A function follows it forever without ever actually crossing it. Okay, and we will see some examples where you might have a graph that looks something like this. Now, this doesn't have any horizontal asymptotes, but it could be possible for a function like this to have a horizontal asymptote that it approaches at the end, but like this middle chunk actually like flips over it. So you'll kind of see that as we go, but that is a possibility. Okay, so most of the asymptotes that we're going to talk about are either horizontal or vertical asymptotes, but we do sometimes have slant asymptotes. Okay, so the slant asymptote happens when the degree of the numerator, so the degree of the polynomial on top, is exactly 1 larger than the degree of the denominator. Okay, so for example, this guy down here, you're going to see the degree on the top is 3, the degree on the bottom is 2, so it's exactly 1 larger. And that gives you your slant asymptote. And you can kind of see it here, right? There's no dashed line, but you see how there's kind of like a line that goes right through this function here? And as we kind of come out here, this function is approaching that that slanty line and the slanty line on this side. So that's what a slant asymptote looks like. For the sake of this course, all we're really going to focus on is figuring out like, okay, approximately what's the slope of the line that that's parallel to. We're not going to really dig into finding the exact equation of the line. Okay, but we'll get to that later. Okay. And then the last piece that we're going to kind of talk about today is a hole. So holes are like these guys here. So what happens with an asymptote is that like an asymptote, you never have a value. So like here, there's an asymptote at -3. So there's no value on that line, right? But it kind of makes the graph sort of split off into separate pieces, right? What happens with a hole is that your function just kind of keeps continuing the way that it is, and then just sort of like jumps over that point. Okay, so that's what a hole is. It's a single point where a function is not continuous. Okay. All right, so we have 3 graphs here, and we're just right now focusing on this vocab and just looking at the graphs and identifying what these different pieces are, okay? So we're not worrying about the equations. The equations are listed at the top, but I don't care about that just yet, okay? So first thing we're going to do is our limit notation, so our end behavior of this function. So what is the limit as this function as my x's are going infinitely larger? Well, you can see that on this side, it's coming down, but it's not going down forever, right? It looks like it's approaching the x-axis. Okay, so what is the limit of this function? Well, it's approaching a y value, an f of x value of 0. Okay, similarly on this side, what is my function approaching as I approach negative infinity on the x's? So as I go towards negative x, same thing, it's approaching 0, right? So my end behavior for this guy, we're approaching 0 on both ends. All right, vertical asymptote, that's this little dashy line. So that's at the equation x equals 2, right? Every point on this line has an x value of 2. This is 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. So they all have x values of 2. Horizontal asymptote is this guy right here, right? That's what's causing our end behavior. So we have a horizontal asymptote. You can't see the dashy line because it's right on top of the x-axis. And honestly, a lot of times in functions, they won't even draw the asymptotes in. Okay, so you just kind of have to be able to look at it and find it. But we do have a horizontal asymptote at 0. All right, well, what's the equation of these guys? Well, this is 0, 0. This is 1, 0, 2, 0, 3, 0, 4, 0. Those are all points with a y-coordinate of 0. Okay, really watch out for the x equals y equals thing. That's the part that trips people up. And then our last bit, our hole for this guy is this point right here. So it's pretty clear that the x coordinate of this guy is 3. The y coordinate, I'm not exactly sure. It looks like maybe it's at 1. For right now, from a graph, I'm just going to say it's like 1-ish. Okay, so that's good enough. It's not exactly 1, but it's 1-ish. And that's close enough for now for what we're looking at. Later, we'll talk about how do you find the exact number. All right, the second guy that we have, okay, so this one, what is my end behavior? Well, as x is getting bigger, what's this function doing? It's going to level off at that asymptote at 3. So my function is approaching 3. All right, what's happening on the negative infinity side? Well, as I come towards negative infinity on my x, it's going to level off again at that asymptote, so at 3. Okay, vertical asymptote, that's this guy right here. Those are all points with an x coordinate of -3. My horizontal asymptote, this guy right here, those are all points with a y coordinate of 3. They all have the same height. Okay, and my hole for this one, so the x coordinate is definitely 3, and it's somewhere between 1 and 2, right? So I'm going to call this like, I don't know, 1.75-ish, and that's good enough for the sake of what we're doing right now. All right, and then this last guy here. Okay, so looking at our end behavior. So this is that one where you've got some kind of a slant asymptote, right? So there's a line that goes something like that, right? Sort of between those that this guy's approaching at either end. Okay, so that's an example of what a slant asymptote is going to look like. So what's our end behavior doing? Well, as my x's are getting infinitely bigger, right? So I'm coming out this way. What's happening? This is going to go down forever, right? It keeps going down, 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 down. There's no asymptote to stop it. So this is going to approach negative infinity. Okay, on this side, so as my x's are going negative, what's happening? This is going up, and it's going to go up forever because there's no asymptote there to stop it, right? There's some sort of a horizontal asymptote, but that horizontal asymptote is going to keep getting bigger forever too. So this is going to keep approaching infinity. Okay, so when you have a horizontal asymptote, your end behavior is going to approach a number. If there's some sort of slant asymptote, we should go back to our infinities. Okay, vertical asymptote for this one actually has 2, right? There's one here and there's one here. So I'm going to have one at x equals -1, and then we'll have another one at x equals 2. Okay, and then our horizontal asymptote, this one doesn't have any, right? There's no spots where this levels out horizontally. So I'm just going to say none. And holes, if there's some sort of a hole on a graph, I will show it to you like this. So if you don't see any of those guys on here, you can just assume that there are no holes. Okay. All right, so this shouldn't feel too crazy overkill. This is just, again, knowing that vocabulary and being able to identify different pieces just by looking at it and understanding what those words mean, okay? Okay, so now what we're going to focus on is how can I actually find the equations of our horizontal and slant asymptotes from the equation, so algebraically, okay? And the big thing with this is it's all about how the degree of the numerator compares to the degree of the denominator. All right, great. So what does that mean? So the degree, okay, when we talk about a degree of a polynomial, that's the highest exponent. So in this little example that we have here, we've got this rational function where in this one, right, the degree of our polynomial on the top is n, and here the degree of the polynomial on the bottom is m, okay? And those are going to be the two things that we compare. All right, so for example, here n is 2, m is 2. This one has an invisible 1 there, so this guy's a 2x to the first power, so n is 1, m is 2. This one, n is 2, this one, m is 1. Okay, so that's all that we're talking about. It's just whatever the biggest exponent is on the top and on the bottom. And then there's 3 cases, okay? Case number 1, if the degree on the top is bigger than the degree on the bottom. Okay, that tells me that there's no horizontal asymptote, so there's not going to be one that's straight sideways, but there is some sort of oblique asymptote. For this class, it's always going to be just a slant asymptote that's parallel to a line. But if you had something where it was, say, like 2 degrees larger, that would actually give you an asymptote shaped like a degree 2 parabola, right? If you had x to the, like a degree 3 difference between them, it would give you a parabola shaped, I'm sorry, a cubic shaped asymptote. So it's just kind of a neat little bonus fact, not important. Okay, so if this degree is bigger than on the top than the bottom, right, and it's by exactly 1, then you're going to have a slant asymptote, and that slant asymptote is going to be parallel to this line. Okay, what the heck is that line? You're going to see this A over B thing coming up, right? A and B are these guys right here. They're the leading coefficients on the top and the bottom. Okay, so it's going to be something that'll be parallel to those leading coefficients. All right, so that's case 1, and we'll do some examples in a second. Case 2, if the degree on the top is smaller than the degree on the bottom, then you have a horizontal asymptote, and it's at y equals 0. Okay, and then case 3, if the degrees are the same, you have a horizontal asymptote, and it's at, again, that same ratio there. Okay, so quick difference, this one, slant asymptote, will be parallel to a line where that is the slope. This one is going to be like a horizontal line at that number. Okay, so this one will be a slope. This one's just the actual like number that line's at. All right, great. So let's do a couple of these. So these guys are right here. So first of all, I'm looking at my degree. So the degree on the top is 2, right? That's this exponent. So n is 2, right? And then the degree on the bottom is also 2. So we have n equals 2 and m equals 2. So that means they equal to each other. So we're in case 3. So that means I'm going to have a horizontal asymptote, which I'm going to abbreviate. And the equation is y equals this ratio right here. So it's y equals 3 over 5. And that's it. Okay. All right. Second case. Okay. This one. So the degree on the top is 1 and the degree on the bottom is 2. So that means that n is smaller than m. Okay. Well, that means that I have a horizontal asymptote, and it's always just at y equals 0 in that case. Lovely. All right, third one, right? Degree on the top is 2, so n is 2. Degree on the bottom, again, that's just a 1. If there's no degree written in, it's just 1. So in this case, n is larger than m. Okay, so that puts us over here. And it's larger by exactly 1, right? This is exactly 1 larger than this one. So I'm going to have a slant asymptote. So I'm going to write SA for slant asymptote. Okay, and it's going to be parallel to y equals this ratio x. Okay, so it's going to have 2 over 5x, right? That slope is going to kind of tilt something like that, right? So it's telling me I'm going to have a slant asymptote that's something like this guy. Okay, and we will focus more about those and what they look like a little bit later. All right, next one. So this one, degree in the top is 1. Degree in the bottom is also 1. So that's a case 3, right? They equal each other. So I have a horizontal asymptote, and it's at y equals 4 over 8, which of course simplifies to 1/2. Okay, you don't need to know which case is which. That's not important. I just called them case 1, case 2, and case 3. That doesn't matter. You just need to know how the degrees relate and what that tells you about your asymptotes. Okay, this guy right here, there's no x's in the top at all. That tells you that your degree is 0. Okay, so if it's just an x somewhere, right, like how in this guy was, it just had x as high as 1, that's a degree of 1. But if there's no variable at all, that's a degree of 0. Okay, and on the bottom part, m is 2. So n is smaller than m, which means I have a horizontal asymptote at y equals 0. Okay, and then this last guy, so that negative that's chilling out in the front, right? When you have a negative in the front like that, most of the time we sort of say, okay, put these two together like it's a -4. That's generally what happens, is you sort of just apply it to the top. Sometimes you might have to do like a distributive property if there's more than one term, but that's generally how things work with negatives. Okay, so the degree on the top is 0 because there's no variable. Degree on the bottom is 1. So n is smaller than m. right? I'm going to have a horizontal asymptote at y equals 0. And that's it. Okay, so that's our first kind of rule here. Okay, that's how you figure out your asymptotes. So the next thing that we're going to do is we're going to write limit notation for our end behavior of the functions. Okay, and if we kind of think back to these guys that we were looking at, end behavior is all about horizontal asymptotes or slant asymptotes, right? So if I have a horizontal asymptote, that tells me that my ends are going to approach that asymptote, right? Horizontal asymptote, my two ends approach it. Okay, if I have a slant asymptote, that's when it's either going to approach negative infinity or positive infinity. Okay, so this whole chunk right here, this is all about asymptotes. So the first thing that we're going to do is figure out, okay, what are my asymptotes for these guys? So this one, n is 3, m is 3. Okay, so that means I have a horizontal asymptote at y equals those ratio of our coefficients. So my horizontal asymptote is at y equals 2/6 or 1/3. Okay, so what does that tell me? It tells me that when I look at my graph, I have this horizontal asymptote here, and the function is going to approach that line on both sides. Okay, so my limit as x is going to negative infinity for my function f of x, right, is just that it's going to approach that asymptote, 1/3. Okay, and similarly on the other side, as x is approaching positive infinity, my function is still just going to approach that asymptote at 1/3. That's it. All right, this middle guy here, n is 2, m is 3. So n is smaller than m. We have a horizontal asymptote at y equals 0. So very similar to the last one, right? I've got a horizontal asymptote at 0 here, right? So my limit as x is going forever negative of my function g of x is that it's always approaching 0. And same thing on the other side. As x is getting bigger, my function is still approaching 0. All right, and then this last one. Okay, so you can probably guess this one's going to have a slant asymptote, right? Because we did one of the other two cases. So in this one, n is going to be 4, m is going to be 3. So this triggers my slant asymptote. So I know that this one has a slant asymptote at this ratio, invisible 1 there, right? So it's a slant asymptote, and it's going to be parallel to y equals negative 3x. Okay, so let's think about what that line would look like, right? Think back to algebra 1, y-intercept would be at the end, and then this is your slope, right? It's telling you go down 3 and over 1, right? So when I think about what this graph looks like, I don't know where my y-intercept is. We don't care about that part, right? But I know that I'm going down 3 and then over 1, and then down 3 and over 1, right? My graph is going to look something like that. That's what the line for that asymptote is looking like. Okay, so when I think about my limits, what's happening as x is going negative forever? Well, if I'm following this asymptote, the asymptote's going up forever, right? So it's going to be forever approaching infinity. Okay, and then on the other side, as x is going bigger, what's happening to my function, right? Well, I'm following this asymptote, which is going down forever, so will my function. Okay, so horizontal asymptote, it's going to approach, your end behavior will approach that asymptote on both ends, right? That is what an asymptote is. Okay, slant asymptote, same thing. It's going to approach that asymptote, but since it's a slanted line, you're going to be either going up forever or down forever, and you just have to figure out like which side is it on. If that had been a positive 3, this would be the exact same thing, except this line would go this way. So then this side would be negative and that side would be positive. All right, and then this last guy. So which of the following has a slant asymptote parallel to that line? Okay, so two pieces that I know from this. Slant asymptote part, right, tells me that I have to be in this first case. So n has to be bigger than 1, or sorry, bigger than m by exactly 1. Okay, so let's look at our degrees. This one, they're equal to each other. So nope, you're out. This guy, n is smaller by exactly 1. Okay, so that's not it. Okay, this guy, bigger by exactly 1. So that's a contender. And then this last one, bigger but by 2. Okay, cool. So That one is gonna have a slant asymptote, but because it's bigger by 2, it's not gonna be a line that it's gonna work out to. It's gonna be something that's like a U-shaped asymptote. So like this one we can kind of eliminate as well, and it's gonna have to be C. All right. The one other thing you want to check is that it's parallel to that 1/2, which indeed it would be, right? There's an invisible 1 here, so parallel to 1/2. All right, so that is kind of our introduction to rational functions. We're just right now starting to look at some key pieces. So you should feel comfortable looking at a graph and identifying all of our different pieces, like the vocab of it. Okay, you should be able to look at a function and find your asymptotes, okay, including a slant asymptote.